Imagine a long and narrow rowboat called a shell. These types of boats are designed for rowers and a coxswain. A coxswain steers and motivates the crew, while the other 8 people in the boat are divided into 4 ports and 4 starboards. In unison, they pull all 8 oars forward, each just inches above the water. Suddenly, the oars twist and drop into the water. As the crew pulls the oar backwards through the water, the boat lunges forward. The crew members are seated on sliding seats where their feet are tied into stationary shoes. Essentially, they are jumping off their foot stretchers with each stroke. The rowing stroke utilizes predominantly the legs and core. A common misconception is that the arms do most of the work. As the rower pushes off their foot stretchers, they pull on the oar, driving it through the water. As the blades of the oar enter the water, the boat seems to lift up in the water and gain speed. At the end of the stroke, all oars lift several inches out of the water and blades are feathered to clear the water. As quickly as it's sped up, the boat slows down as it coasts. Then once again in unison, the oars twist and drop into the water. The process repeats stroke after stroke. Physics is involved in every aspect of the stroke, from the angle of the rigging, which is often tailored to the person rowing in each seat, to the balance of ratio that comes from building boat speed gradually to allow the boat to move under the rower on the recovery portion of the stroke. At practice, we often reference boat acceleration. How does a boat accelerate? A boat accelerates through the action-reaction principle of Newton's third law. You move water one way with your oar, the boat moves the other way. The momentum, which equals mass times velocity, you put into the water will be equal and opposite to the momentum acquired by the boat. Consider a boat before and after a stroke. Before the stroke, total momentum equals 0, since everything is at rest. After the stroke, total momentum, which would equal the mass of the boat times the velocity of the boat, minus the mass of the water times the velocity of the water, will equal 0, because the total momentum can't change. This is Newton's second law. During a stroke, it is less obvious that water is moved backwards in order to keep the boat moving forward, since the blades appear to lock in where they are placed. But if you look at the puddles when the blades are extracted, it's clear that water is moved. Our second component of the stroke to focus on is the center of mass within the boat. A rowing boat is not a solid body. It contains 3 separate components. The first is the crew, representing 70 to 80% of the total mass. This is the mass of each rower combined. The second component is the boat itself, including the coxswain, representing 20 to 30% of the total mass. The third component is the oars, representing less than 5%, which we will ignore for today. The center of mass of the whole system is the mass-weighted average of the positions of the center of mass of each component. While the individual component center of masses can move relative to each other, the center of mass of the whole system cannot change its momentum or velocity unless external forces are applied via the water usually. This is representing Newton's first law. If a crew mass mc is sitting still at backstops in a boat mass mb moving at a velocity, the total momentum of the system will equal mc times vc equals mb times vb. This equation explains why when a crew moves towards the stern at negative velocity of the crew relative to the velocity of the boat must move towards the bow at a different relative velocity to conserve momentum. Let's say the crew represents 80% of the total mass. This means that the mass of the crew is 4/5 of the mass of the crew plus the mass of the boat. Then the mass of the crew equals 4 times the mass of the boat. This gives us the velocity of the boat equal to 4 times the velocity of the crew. If the crew moves towards the stern at a velocity of 0.2 meters per second, the boat will move towards the bow at an extra 0.8 meters per second. In 1 second, it looks to the crew that they've moved 1 meter towards the stern of the boat, but to an outsider it looks like 80 centimeters of that movement was the boat moving towards the crew. This is why, to a spectator, the bow of a boat appears to surge after the finish of a stroke. Although the blades have come out of the water and are no longer accelerating the center of mass of the whole system, the crew's movement off their backstops accelerates the boat forward by an equal and opposite reaction. As you can see, the rowing stroke is comprised of 2 fundamental points: the catch, where the blade of the oar is placed in the water, and the finish or release, where the blade is removed from the water. As the rower brings the blade through the water from the catch to the finish, it is called the drive, and as the blade returns from the finish to the catch, it is the recovery. There are several components of physics that can explain how this process works. Center of mass and acceleration are just 2 examples.